This is me re-recording the beginning of class from this morning because I forgot to hit record. So we want to talk a little bit about angle and orthogonality. So the first thing we mentioned in that video that I asked you to watch for this section is the Cauchy-Schwarz inequality. So the Cauchy-Schwarz inequality relates the dot product, the inner product of two vectors, with the magnitude of the two vectors. And it says that if you take the absolute value of v and w, the inner product of v and w, that's always less than or equal to the product of the magnitudes of the two vectors. And it's going to make some nice things work for us. We'll see one of those here later on in the proof that I want to make sure that you got, that I mentioned in class today. The other thing that makes work is the angle between two vectors in any inner product space. So along these lines, let's look at some properties of length and distance. This is on page 308 and 309 of your text, and specifically these are theorems 6.2.2 and 6.2.3. They're related to each other because we're talking about the properties of magnitude, properties of length, and distance is defined in terms of length. So these properties 1 and 2 go together. They say that the length of a vector, the magnitude of a vector, is always non-negative, and the only way it can be 0 is if the vector started out to be 0. So in that perspective, the reason for that, why that works, is remember that the magnitude of a vector is always equal to the inner product of the vector with itself. And we know from property 4 of inner products that when you take a inner product of a vector with itself, you always get something that's not negative. It's why you're able to take the square root in the first place. And on top of that, also according to the axiom for inner product spaces, the only way that this can possibly be 0 is if the vector started out to be the 0 vector. So properties 1 and 2 are basically just a statement of axiom 4 in the language of lengths. Property 3 here says that if we have a scalar times a vector, the magnitude, if we pull the scalar out, we get an absolute value. This is also pretty straightforward. If I want the magnitude of a scalar times a vector, that'll be the square root of the inner product of that vector with itself. Axiom 3 of inner products is that we can pull a constant out of a component and put it in front of the inner product. We have one in the first component and one in the second component. So when we pull them both out, we get a k squared. Now when we take the square root of the k squared, we get absolute value of k. And when we take the square root of the inner product of u with itself, we get the magnitude of u. All right, so the fourth one here that we have is referred to as the triangle inequality. So the triangle inequality, the reason why we call it the triangle inequality is if you remember if you've seen drawing out vectors in Euclidean space, we know that we can do vector addition by taking one vector and then putting tip to tail, if you will, for the other vector for v. So do u and then do v. And then if I take the one that starts at the initial point of u and ends at the terminal point of v, that is u plus v. And this is the reason why it's called the triangle inequality. You probably remember from your geometry class in high school that the sum of any two lengths, the sum of lengths of any two sides of the triangle is always greater than the third length, the length of the third side. So if I take the length here of u and the length here of v and add them together, it better be the greater than or equal to the length of u plus v. All right, so let's see how this proof works. A lot of times when you do proofs with norms, with magnitudes, you usually start with the square and then do square roots at the end. It just makes the algebra tend to be easier rather than having to deal with the square roots each time. So the magnitude squared is just the inner product of the vector with itself. And now using the properties, in particular axiom 2 for the inner product, we know that we have left distributivity and right distributivity over sums in the components, and basically you get what looks like a FOIL. So when you multiply, when you do the inner product, I mean here, you'll get u inner product with itself. That looks kind of like a u squared, if you will. You get a 2 times the inner product of u with v. Those would be your outer and your inner terms. And then you have to use the commutativity property for inner product there. And then your last terms would be v inner product with itself. All right. So now we look at, we see this the inner product here in the middle. We know from the Cauchy-Schwarz inequality that I can replace that with its absolute, no, sorry, no, that's not Cauchy-Schwarz yet. If I replace that inner product with its absolute value, all I've done is potentially make the sum bigger. Right? Because if this is negative, then it certainly makes it bigger when I take the absolute value. And if it's positive, I didn't do anything. So the only thing I could have possibly done was make it a little bit bigger. Can't make it any smaller. And then Cauchy-Schwarz inequality says if I replace it with the product of the magnitudes, it still might be, you might get the bigger, even bigger still, but certainly cannot get smaller. So I still have less than or equal to there. And now in terms of the first two, the first and the last one here, this is the magnitude of u squared, and this is the magnitude of v squared. And now I notice that this is what looks like a FOIL again. Looks like I can refactor it as a binomial squared. If you think about an x squared, an x plus y squared, I mean, that's what this looks like if this is my x and this is my y. So this is greater than or equal to the magnitude of u plus v squared. And now taking square roots gives us the result that we want. All right, for distance now, this is all, these distance ones are all true because of the fact that they're all defined in terms of magnitude. Remember that the distance between u and v is the magnitude of the difference of u and v. Well, if it's a magnitude, certainly the distance is always greater than or equal to 0. The only way the magnitude can be 0 is if the vector itself is 0, which would require u and v being the same here. This property here, where the distance from u to v is the same as v to u, is just basically a restatement of this absolute value property up here. V minus u is the negative of u minus v, and if you pop out a -1 and take its absolute value, it stays the same. This one is a restatement of our triangle inequality again. If I take the magnitude of u minus v, I can do our tried and true trick of adding and subtracting the same thing in the middle. So take any vector w, put it in the middle, and now use what we just proved about the triangle inequality above. This is less than or equal to, is split it at the plus sign, it's less than or equal to the u minus w plus the magnitude of w minus v. Which is exactly what, these are just statements of how the distance is defined. So those are the properties of length and distance that we talked about at the beginning of class. And again, I really wanted just to give you this proof with using the Cauchy-Schwarz inequality again for this property 4. That was the big thing I wanted to go through. That's also still in your book. It's on page 309. All of these properties are listed on page 309. But again, like I mentioned, notice that the distance properties are basically restatements of the length properties.